So in order for us to move from Bohr to the current model, we had to change our perspective. And so that's exactly what we did. Um, Bohr worked really great for hydrogen, but really only hydrogen. So what we did was we moved to the quantum mechanical model of the atom. And this was based on the wave properties of matter itself. So what happened was de Broglie kind of picked up on Bohr's model and ran with it. He expanded it. Because remember, Bohr only worked for hydrogen. So we needed to have some sort of model that worked for all atoms and not just one. So he realized that the way that our electrons' orbits behaved were more like waves. And so what he suggested was that electrons actually could be considered waves confined to the space around the atomic nucleus. And so he created what we call the wave-particle duality of nature, whereby light and electrons both have properties of waves and particles. And we can use mathematics actually to describe both of them. So it is the ultimate pleaser. Okay. Then came along Schrödinger, and he used this dual wave particle nature to develop a mathematical equation using differential calculus that actually treated the electrons in atoms as waves. He basically used this equation to generate 4 quantum numbers, and it described the electron's behavior as well as its location in the atom. So it may sound weird that we're able to get these 4 quantum numbers from a single equation, but if you look at an equation like x squared equals 4, we actually have 2 possible answers, -2 and +2. So it's not really that much of a stretch to think we could get 4, although his equation is obviously much more complicated than that. But what his numbers do is they actually give us the address of each electron in the atom. So it allows all of these different electrons to exist. It allows us to describe their behavior appropriately, and also for them to have a location where they can be without crashing into each other. All right, so basically what this is the quantum model, and it mathematically describes the wave properties of electrons. It describes the probability that an electron is found in a certain location around the nucleus, and this probability is viewed as a cloud. Within this cloud, there is an orbital, and that is a region where the electron with a particular energy is likely to be found. Okay, so one other thing we need to understand is Heisenberg's work here and his Heisenberg uncertainty principle. He basically said that we can't know the exact location and momentum, a lot of times I say speed, of an electron at the exact same time. So that may sound weird, but the idea here is that the electrons are moving so fast that by the time we find an electron and know where it is, we've changed the direction and also the speed that it was going. And by the same token, if we find the speed and where it is going, the direction and speed that it was going, we've changed its location in order to do that. So we can't find both of those things simultaneously. He was extraordinarily brilliant. He actually was only 23 when he proposed his principle, and he did do some of his postdoctoral work with Bohr. So bear with me here as we go through the different quantum numbers and, kind of try to relate it as much as possible to things that you guys know. So, I forgot I had this cartoon in here, sorry. This is a Dilbert uncertainty principle applied to an office scenario. So kind of funny, haha. All right, so quantum numbers. So quantum numbers provide more specific information on the probable location of an electron. And remember, each electron has its own unique set of quantum numbers that describe it. The thing is that no 2 electrons have the exact same quantum number. No 2 electrons have the exact same address because they can't exist in the exact same way. So we have 4 quantum numbers. The first one is the principal quantum number. This corresponds to the energy level, and it describes the relative size of the electron cloud. It's described by n, and n is a positive integer, 1 through 7. So 1 is the lowest energy, 7 is the highest energy. Now, you can actually relate this, and you know the n of any electron by simply looking at the position of the element on the periodic table. we only have 7 periods. So n corresponds to the period where that atom sits. So all of the electrons in an atom will have the same n number, and that's normal. As n increases, actually that's not completely true because they will have each atom has its own unique set, so you can actually have n1 through like n7 in if I have something in the 7th period, whereas something in period 4 can only have 4 n, so it would be n1, 2, 3, or 4. So, but as n increases, the electron's energy and distance from the nucleus increases. So the higher the n, the further away from the nucleus it is. The maximum number of electrons an energy level can have is 2n squared. All right, the second one is the sublevel, and this is the angular momentum. Its symbol is a lowercase l. So how many sublevels you can have is n minus 1. And this is basically used, and we don't really think of it as angular momentum. What we think of it as is shape. So this sublevel describes the shape of the area where we can actually find the electrons. So n is how far away it is from the nucleus. Sublevel is the shape within it that it can exist within. So you can see here we have different symbols. S stands for sphere, P stands for peanut, D stands for double peanut, F stands for flower. Okay, and if n is 1, I can only have an S. If n is 2, I can have both S and P sublevels. If n is 3, I can have S, P, and D. And if n is 4, I can have all 4 S, P, D, and F. Okay, keep in mind that if I'm at n equals 4, I have not only the sublevels at 4, but I also have all the sublevels at 3, all the sublevels at 2, and all the sublevels at 1. But you can see here then how my L, my angular momentum, is different. The shape with the lowest energy is the S. Okay, the shape with the highest energy is the F. Now, what we can do then is we can go ahead and take a look here at some of those shapes. So the S sublevel is spherical, just like its description. P is peanut. Okay, I almost kind of describe it as a dumbbell shape. D is kind of complex. The first one looks kind of weird, but you can see how it kind of looks like a double peanut in its shape. And then this looks like F. F is very odd and very strange. The first three are very different, but you can definitely see with the last 4 how they have kind of that flower shape. Okay. So if I took all of them though and I combine them, you can actually see now each color represents something different, whether it's S, P, D, or F. But you can see how we kind of get the general spherical shape of the atom overall when we put them all together. But notice that none of them overlap. Each of them have their own space, and what that does is it allows all of our electrons to exist together without crashing into each other and degenerating the atom. Our third quantum number is our magnetic quantum number, and this can equal between -1 to 0 to +1. So, for example, I can have an electron with a principal quantum number of 2, a sublevel of 1, okay, and my magnetic quantum number of -1, 0, and +1. Basically, it describes the direction in space. Okay, it tells us how many orbitals are in that sublevel. Okay, so magnetic quantum number is how many orbitals are in that particular sublevel. So with a sublevel of S, I can only have one direction. I have one orbital. With P, I have 3 directions. Okay, and I have 3 orbitals. With D, I have 5 directions. You see them listed here, and I have 5 orbitals. F, I have 7 directions with too many detailed names, and I have 7 orbitals. So basically, if we go back to my sublevel, okay, each sublevel, the sublevel that is present depends on my principal quantum number, and the sublevel that is present is going to tell me how many orbitals I can have. All right, now each orbital can only hold a maximum of 2 electrons. So let's start with that idea here. So for instance, at an S sublevel with 1 orbital, I can only hold 2 electrons. At a p sublevel with 3 orbitals, I can hold 6. With a d sublevel with 5 orbitals, I can hold 10. And with an f sublevel with 7, I can hold 14. Now, orbitals sometimes exist in the same sublevel and end up with the same energy, and they are called degenerate orbitals. And so this is sometimes what we call orbital hybridization. And you can actually see this here with this particular one. So I have this particular orbital here, okay, and then I have some additional orbitals. When it's overlaid, they actually create the exact same energy levels, so, or the exact same energy, so they hybridize, and that's what that is doing there. So I take kind of the P shape here and the D shape, and they actually kind of hybridize and they degenerate. The last quantum number we have is for mathematical completeness, and that is our spin quantum number, and that is the direction that the electrons spin in a particular orbital. So because each orbital can only hold 2 electrons, if they both spun in the same direction, it would actually rip the orbital apart and the atom would collapse on itself. So in order to do that, the 2 electrons in the same orbital have to spin in opposite directions. It's actually kind of a balance thing. So we can have an up spin, which you can see here kind of looks like it is counterclockwise. And then we have the down spin, which again, if we look at it from the top, would be a clockwise spin. Okay, these 2 spins balance each other. It keeps the atom from wobbling, and it keeps the atom from getting torn apart. Now, I can have electrons in different orbitals that have the same spin, and those are called parallel spins. So, what you need to understand is we have these 4 quantum numbers. Principal quantum number relates to the period. Sublevel, which relates to the shape of the orbital cloud. You've got the magnetic quantum number, which basically tells us how many orbitals we can have in a sublevel. And then we have the spin, which is for mathematical completeness. What we will do is we will actually put these together with our electron configurations and most of these ideas, and put them together with electron configurations next time.